Hi, I'm Amy. Let's take a look at some limits as x goes to infinity and talk about the end behavior of those functions and whether or not they have horizontal asymptotes. When you're looking at a limit as x goes to infinity, what you're really doing is looking at what happens at the extreme ends of the function. When x gets really, really big, positive infinity, and x gets really, really far out in the negative direction, towards negative infinity. That's referred to as end behavior. What is the graph doing in either of those directions? Well, a lot of times you'll have a graph that's unbounded, meaning it just keeps going up, 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 or down, down, down. And a lot of times you might come across a graph that has a horizontal asymptote. We're going to focus on those two possibilities of end behavior because those are what are going to come up most often for you in your calculus class. So first off, let's look at the graph of y equals x squared. It's just a plain old parabola, right? What does that function do at the extreme ends of the x-axis? So I'm going to do just a terrible little sketch here of y equals x squared. So as x goes off in the negative direction, x is approaching negative infinity, where is the graph heading? Well, this arrowhead right here tells you that graph is heading up, up, up. It's not coming back down. It's not approaching a horizontal asymptote. It's approaching infinity. So we can write positive infinity because that's where the graph is heading. And of course, that would be a limit that does not exist because the limit, we never reach it. You don't ever get to positive infinity. A limit implies there's a cap, there's a place that we're getting really close to reaching. In the positive direction, as x approaches positive infinity, again, you see that arrowhead saying this is going up, up, up. So again, we're going to positive infinity and the limit does not exist. So to recap, infinity is not a numeric value. So we have to say that the above limits do not exist. Also, since infinity isn't a numeric value, we can't use an equal sign. You'll notice above here, I use these little arrows to imply we're getting closer and closer to positive infinity, but we don't ever actually equal infinity. Now, if we look at this limit from a more algebraic point of view, we can think about plugging in a value for x. For instance, as x goes towards negative infinity, think about taking negative a billion, for instance, and putting that into the function x squared. When you square negative a billion, you get positive something gigantic. So we have affirmed that that limit really is going towards positive infinity. It is unbounded. That limit does not exist. Same thing as x goes to positive infinity. When we go and take a number like positive a billion and put it into the function x squared, we get an even larger positive gigantic number, again confirming that our limit goes towards positive infinity and our limit does not exist. Next, let's take a look at another function. This time I've got a nice rational function, f of x equals 10x squared plus 3 over 2x squared plus 9. And what we're going to do is we're going to investigate the limit as x goes to infinity of this function. So what that means is we're going to find out what happens as we go way, way, way out on the right as x approaches positive infinity, and what happens way, way, way out on the left of this graph as x approaches negative infinity. And for a nice rational function like this, I like to use what I call the dividing technique. And as you get better and better at it with more experience, you'll kind of find your own way of doing this. But I like to look at the function and say, what's the highest power of x that I see? And I see x squared as the highest power of x. In fact, it's the only power of x in this particular problem. So I'm going to rewrite limit as x goes to infinity because we're still figuring out what the limit is. And I'm going to go through and I'm going to divide. I'm going to divide each and every term by that x squared. So that leaves me with 10x squared over x squared plus 3 over x squared in the numerator. And then in the denominator, I've got 2x squared over x squared plus 9 over x squared. And what you'll see is I have a couple of x squareds over x squareds. There's places where I can reduce. For instance, x squared over x squared equals 1 here, and x squared over x squared equals 1 here. So what I'm left with then is the limit, as x still is going to infinity, of 10 plus 3 over x squared over 2 plus 9 over x squared. And now I want you to look at 3 over x squared, and 9 over x squared. As x goes to infinity, as x gets really, really, really large in the positive direction, or actually really, really large in the negative direction as well, what happens when we square it? Well, that denominator gets gigantic. This denominator gets gigantic. So each of these individual fractions, 3 over gigantic, 9 over gigantic, both of those fractions become so tiny, they're practically 0. Now, are they equal to 0? No, but they are practically 0. They're heading towards 0. That's what these arrows are implying. They're heading towards 0. That means our overall limit is equal to 10 over 2, which is 5. Notice I didn't write the limit notation anymore because we found our limit. Our limit is 5. Now, looking at the graph of this function, and this isn't one that I would off the top of my head know what it looks like, but we can figure out that the y-intercept, if I plug in x is 0 here and here, my y-intercept is going to be 1/3. And my horizontal asymptote is where the limit was, right? I have a horizontal asymptote at y equals 5. So I'll put in a dash, 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 dash. That's y equals 5. Now there's lots of other stuff that you would have to figure out to know the exact shape of the graph, but it looks something like this, where we have, and again, not a great graph, but we're showing we have asymptotic behavior both off towards positive infinity and towards negative infinity. But all in all, we found that we have a horizontal asymptote because we looked at the limit as x goes to infinity. So let's look at a few more examples of the dividing technique. This next problem asks if this function f of x has a horizontal asymptote. Of course, anytime you're looking for a horizontal asymptote, that means you need to investigate the limit as x goes to infinity. And once again, we have this nice rational function, and I'm going to use the dividing technique. I'm going to find that highest power of x, I see x cubed, and I'm going to divide each and every piece by x cubed. Now, I'm going to fast forward through this a little bit, so feel free to pause the video so that you can keep up. So now you'll see I have written the limit as x goes to infinity, and then I have every single original term over x cubed. So I've divided everything by x cubed over x cubed. I'm really just dividing by 1. So it changes the look, but not the value of the overall limit. So the point of this is, what can we reduce so that we can find those little fractions that go to 0? And you'll notice x cubed over x cubed, x cubed over x cubed, both of those cases, the x cubes cancel out altogether. They go to 1 in each case. In the rest of the cases, you'll have some reducing to do. For instance, 2 of the x squareds on top leave you with a single x on the bottom. So I'm again going to fast forward through this so that you can see what the next step is. So after I've gone through and done all my reducing, you'll see that I have a bunch of little fractions left. I have these fractions and these fractions, each of which has a number on top and an x or some power of x in the denominator. Each of these fractions is a number over x. X is going to infinity, so they're each a number over something gigantic. In each case, each of those fractions are heading towards 0. And what I'm left with is 5 over 3. So my overall limit is equivalent to 5/3. So does my function have a horizontal asymptote? Yes, it does. Yes, it does, and that asymptote is at y equals 5/3. Another way some people look at this type of problem is to notice that the power on the numerator and the denominator, they have the same degree. They have equal amounts of infinity going on there, right? Third power and third power. And everything else is such smaller powers of infinity that they practically don't matter. So in the end, we end up with that 5/3. You'll see that come into play in the other examples I have for you as well. Let's take a look at this example, the limit as x goes to infinity of this lovely rational function. This time you'll notice that the power of x is less on the top than it is on the bottom. I'm going to go ahead and do the dividing technique here as well, but then we can talk about the result and what really is going on here. So again, I'm going to fast forward through. This time I'm going to go ahead and divide everything through by x cubed, the highest power of x. So you can see I've gone ahead and taken every single term and divided through by x cubed. That's basically dividing by x cubed over x cubed. I'm dividing by 1, I'm changing the look, but not the value of the function. And now we're going to go through and see where can we reduce. For instance, here x cubed over x cubed gives me a 1. Everywhere else, I'm going to reduce and I'll have some x's left over. Again, I'm going to fast forward to that point. Now that I've gone ahead and reduced, what you'll notice is almost every single term left is a fraction. The entire numerator is made up of fractions, and these two parts of the denominator are made up of fractions. And remember, each of those fractions is some number over something gigantic. X is going to infinity, so it's getting gigantic in the denominator, which means each and every one of those little fractions is heading towards 0. And if you notice, that means the entire numerator is heading towards 0. So what our limit is equal to is 0 on top and a 3 on the bottom, which just means 0. Our limit is 0. That means that our function has a horizontal asymptote at y equals 0. Now, if you look at the powers again, you'll notice that the power of x on the top, the degree was only 2, and the degree of the denominator was 3. So basically, we have more infinity in the denominator than we did in the numerator. So the denominator wins. The denominator is gigantic, and there's something lesser on the top. And usually if you have something over gigantic, that will go to 0. And look, we got 0 as our asymptote. I'm going to make this next example a little bit quicker. Once again, we have the limit as x is going to infinity. Once again, we have a rational function. I'm going to look, what's the highest power of x that I see? I see x cubed. So I'm going to go ahead and divide each and every piece by x cubed, and then I'm going to go ahead and reduce. So again, I'll fast forward through those steps so you can see them. There it is, and now we'll reduce. Now that the function is finally reduced, you'll see that almost every piece is a fraction. These 3 in the numerator and the entire denominator, all of those pieces are heading towards 0 because the numerator is a real number and the denominator is blowing up. And so what are we left with? We are left with 5 in the numerator and a 0 in the denominator. Really, it's not exactly 0, right? It's something teeny, 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 tiny. So 5 divided by something teeny, teeny, tiny goes to infinity. So in fact, this particular function does not have a limit, right? That limit does not exist. DNE for does not exist. And if we're thinking about the end behavior, we don't have an asymptote, we have unbounded behavior. Let's look at the original problem again, remembering that x is going to infinity. Look at the degree of the numerator, it's 3, which is higher than the degree of the denominator, which is 2. There's more infinity in the numerator than there is in the denominator. So that confirms that our overall limit is going to infinity, which of course means it does not exist. So let's use that idea of the powers on these last couple problems. So we're sort of shortcutting through the dividing technique. Again, we've got limit as x goes to infinity. In this first example, the power on top, the degree of the numerator, is higher than the degree of the denominator. So in this case, there's more infinity on top, and so we're going to say that overall, this limit goes to infinity. And we also would say it does not exist. Notice I covered over the equal sign because nothing ever actually equals infinity, so it's more appropriate to use an arrow. On the next example, again, we're going to infinity, but this time we have the higher degree in the denominator. So the denominator wins. The denominator is the gigantic thing. So if you think about the aftermath of the dividing technique, we'd have basically zeros on top and this giant value on the bottom. So that means that this limit goes to 0. And then finally, I have another example where the degree on the top and the degree on the bottom match. There's the same amount of infinity on the top and on the bottom. So this time we want to look at what are the coefficients. And here I have a 2 and a 4. If you think about the aftermath of the dividing technique, all that's going to be left, other than a bunch of little zeros, which would come from those guys, all that's left is a 2 and a 4. So our limit is equal to 2/4 or 1/2. So I would say for the last problem, we have an asymptote horizontally at y equals a half. This problem has an asymptote horizontally at y equals 0. And this problem does not have an asymptote. It has unbounded end behavior.